Welcome back to chapter 1. We have gone over the prologue and the first half or so, maybe 2/3 of chapter 1. And we are finishing off with the third type of experiments, third type of research that is done in psychology. This is the most popular type of research. It's the most specific to address what we call causation, to say that one thing causes another in psychology. We have to use what's called an experiment. In this case, researchers can focus on the possible effects of one or more factors in several ways. In a descriptive, all we're doing is sort of taking notes and describing what we're seeing, or taking their opinions down or their thoughts on who they're going to vote for, or why they like brand X over brand Y, etc. Trying to describe the person or situation. With a correlation, we are trying to determine if there is a naturally occurring relationship that exists between these things, like self-esteem and depression, height and weight of a child, temperature and amount of clothing that people wear, right? Things like that. Vaccinations and autism, if you will. And if you do get a very high positive or negative correlation. Now, I also want to point out from the last lecture that negative correlations do not mean bad. So if we're looking at a relationship, it's just the nature of the relationship. If two things increase together or decrease together, it's a positive correlation, 0 to 1. If two things, one thing increases and another decreases, or vice versa, that's a negative correlation. So if you have a positive 0.9 or a negative 0.9, the correlation is just as strong. What positive or negative tells you is just whether or not things are going the same direction or opposite directions. So they're just as strong as one another. But the stronger, the closer to 1 or negative 1 that a relationship is, the more perfect the correlation, the more that we can presume that maybe one thing does cause another. If we just do a correlation, if we say that there is a correlation between studying and doing well on exams, and that correlation is pretty high in the fact of those that studied and got a higher score, then we can say maybe one does cause the other. But we can't determine that, like I said, from a correlation. We can only determine that from an actual experiment. So in this case, one of the variables is called the manipulated or independent variable, and we can, as researchers, can manipulate that factor of interest, which means if we're looking at studying, we can split you up into 2 groups, studying or not studying. We can split you up into 4 groups by the amount of studying, 0 hours, 1 to 2 hours, 3 to 4 hours, 6 hours or more. We can measure the other one, right, which is your score on an exam. And we have to control for other factors. When we went over at the end of last lecture, when we went over the idea of self-esteem could cause depression, depression could cause self-esteem. In this case, we are saying that A causes B, so A has to cause B. Studying causes you to do better on an exam. And in order to make sure that the groups are equal, we don't have to do this in a correlation, we control for the other factors. So one of the things I pointed out in the last lecture is that I said if we were going to do this study in class of half of you study 6 hours a week, half of you study 0 hours a week other than watching these videos and reading the slides over once, then we take the exam. I want to control for anything else that may cause a problem. In the last slide of the last chapter, it said that something else, like your bae breaking up with you, saying it's not me, it's you, you suck, I'm out of here, could cause both low self-esteem and depression. We don't want some third factor, some other thing, looking at the relationship between two things. In this case, we're saying A causes B. Studying causes you to do better on an exam, not how much sleep you got, not what you ate for breakfast, and not how much caffeine you had. So to control, we hold all the other potential variables or factors constant. So everybody gets the same amount of sleep if we can control for that. This is why we use a lot of times an artificial or lab setting, because we can control for these things. In naturalistic observation, we can't control for what time of day it is, what the temperature is in there, right? Whether it's distracting or not for people. In a lab setting, we can control for how much sleep you get, what you eat for breakfast, what time of day it is, how hot it is, whether there's lights on or off, shades open or closed, right? So we can put you into two different groups. An experimental group, which gets the actual treatment, so you do the actual studying, and the control group, which is not manipulated in any way. So normally, before this class, you didn't have to study psychology. The control group would be the no studying group. The experimental group is the one whose effects we want to see. So saying that a researcher can manipulate the factors, that just means I can put you guys into whatever groups I want. If there's 40 of you, 20 of you will be in the experimental group where you study 6 or so hours a week. 20 of you will be in the control group where you do no additional studying, right? So that's the idea behind this. So the control group is the group that gets no manipulation. In that study that we talked about in the last lecture on sleep boosts memory, if we were to make that into an experiment, those that get their normal amount of sleep, so nothing changes, that's the control group. The one whose sleep we interrupted so they don't sleep or they only sleep 90 minutes, that's your experimental group. Hopefully you're following along. We also have problems with bias in these settings, and I will actually see if I can find a video for you guys looking at this. But a lot of times the researcher or researchers, experimenters, they are biased and they don't even know it because it's natural, right? They want their theory to be correct. They want their hypothesis to come true. So sometimes there is a potential for bias and they don't even know it. Let's say, for instance, that I was doing a study. I invented a new antidepressant, and of course, I wanted to make money, right? So I'm going to do a study with people that have depression. Half of them are going to get the actual antidepressant that has the actual drug in it, and half of them are going to get something we call a placebo. The placebo is a pill that looks, feels, tastes, everything like the actual drug, but it doesn't have the antidepressant in it. It's just a sugar pill. So the control group would be the ones getting the fake pill, and the experimental group would be the ones getting the actual pill that has the antidepressant. And of course, I want it to work. So I may accidentally be biased in how I hand it out, right? So this would be me handing out just the general control group placebo pill. And of course, you guys or the people in the study should not know who got what. So if I were to go, here you go, here's your pill, right? Just in a regular tone, that would be the one that is fake. And then for the ones that are the actual pill, I could be like, here you go, here's your medication, right? And so in that case, I could be giving away without even realizing it so that the people know which group they're in. And if you guys know which group you're in, or those participants know what group they're in, oh, I got the real pill, oh, I got the fake pill, then they may answer in the way that you want to hear. Those that got the pill that has the actual medication may say, well, I'm supposed to be less depressed, so I'm going to report being less depressed. And those that got the fake pill, the placebo, may say, well, I know this isn't the real pill, so I'm not going to report it. That's a problem, because not only are you biasing, you're being biased yourself accidentally and not even realizing it, but you're also biasing the participants because they know what group they're in. So a lot of times, to eliminate this bias on both sides, we use what's called a double-blind procedure. Neither those in the study nor those collecting the data know which group is which. So in this case, what I would do is I would hire an assistant to hand out the pills to random people. That way, the assistant doesn't know who's in what group, and the participants then don't know who's in what group, and everybody just gets a pill, and they don't know if it's the real one or the placebo. That way, the treatment's actual effects can be separated from the potential placebo effect. And of course, the placebo effect is an effect that involves results that are caused by expectations alone. We'll talk about a little bit about that when we get into the chapter on drugs, chapter 3, and alcohol and things like that. If you guys wanted to run a placebo effect, it is the summer. There may be family gatherings, maybe smaller ones than we're used to. But a lot of times with family, there is beer drinking going on. And even if you guys are not of legal age, I don't care about that stuff. And I would never narc on you. But let's just say that you're getting a beer for a brother, cousin, aunt, uncle, mother, father, grandparent, whatever it is, right? And if you have one of those red Solo cups, instead of handing them the can or bottle of beer, let's say that you went out and bought some O'Doul's, the non-alcoholic beer. I think they have a Heineken 00 now. And you were to give them in a red Solo cup or whatever, you were to pour the beer into the cup and then give it to them. In this case, they're expecting a fully alcoholic beer, but you're giving them non-alcoholic beer. So you give them 2 or 3 of those, and all of a sudden they start stumbling around and acting all drunk. Then you know that you've just activated the placebo effect. But just don't tell them that I told you to do that, because then I get in trouble, right? So you didn't hear that from your professor. But that would be a way for you to run your own experiment using this placebo effect. If that family member or person acts drunk because they expect there to actually be alcohol in it, and remember, those beers taste just like beer with alcohol in them, they just don't have alcohol, then you know that they're acting on the placebo effect. So could be kind of fun. You might get in trouble. I don't want anyone to hurt you. So just saying. So in an experiment, we have one manipulated factor or variable called the independent variable. That is the one that's manipulated. That's the groups that you're being put into, the variable whose effect is being studied. And sort of the cheat sheet way, because you're going to need this for the example I give you guys for the first homework, is the independent variable is whatever groups that you hours of studying, half of you would be put into the group that studies 6 hours or so of studying. So what would I call both of those groups together? Whatever I would call both of those groups together, that's your independent variable. So 0 hours of studying versus 6 hours of studying. What would I call those groups together? Amount of studying, or you could say number of hours studying. That is my independent variable. For the sleep one, we would have people who sleep their normal 6 to 8 hours and people who sleep 0 hours or 0 hours to 0 minutes to 90 minutes. In that case, what would I call that? Number of hours sleeping, right? Or number of minutes sleeping. That would be my independent variable. If we go on this antidepressant versus placebo that I just came up with, right? My control group is 0 milligrams of antidepressant, and maybe my drug, my actual experimental group is 50 milligrams of this drug. You could call it amount of drug, right? Amount of sleep, number of hours studying, whatever you want to call it. Both of those groups together, whatever you would label them both, is your independent variable in this experiment. Let's skip the middle one right now and go down to the dependent variable. In the correlations, you're measuring 2 things. You're measuring the height and weight of a child. You're measuring the temperature and the amount of clothes that they're wearing. So you basically have two measured variables or two dependent variables that you put together, and they are they're put together to see how much they're related. In an experiment, you have one independent variable. Those are the two groups that you put people in, or the groups, and you have a dependent variable. The dependent variable is the measured variable. It's also known as the outcome variable. Just like there's a cheat sheet way to remember the independent variable, whatever the two groups are together, whatever you call that. The dependent variable is whatever number you are getting from the study. So it is the variable that may change. It's called the dependent variable because what score you get or what number you get depends on what it depends on what level of the independent variable. So if we were to use the example that your score of your exam, how high you score, depends on whether or not you studied, right? So the dependent variable would be that number that you get out of it. So whatever number you get. In the studying example, it's the number correct on the exam out of 50 points. In the sleep chapter, it's the sleep study, it's, you had a list of 20 words, so it's however many of those words you remembered correctly. And, maybe for the antidepressant, you do some sort of number on a depression test, and hopefully that number gets lower if you took the actual antidepressant. So that's your dependent variable. The confounding variables in the middle here are factors other than the IV that might produce an effect. Like you may get a better score on your exam if you're better caffeinated. Caffeine, these confounding variables, you don't want to interfere with the relationship between the IV and the DV, or independent and dependent variable. So you want to hold them constant. In this case, nobody gets caffeine because that could be an advantage. Everybody gets the same amount of sleep because you may get a lower score if you don't sleep as much. Everybody eats a bowl of oatmeal for breakfast because we don't want some people eating healthy and some people eating nothing, or some people eating just pure sugar, because those might cause a difference in the scores. But we are saying that A causes B. And in this case, what we're really saying is A and only A causes B, and not C, D, E, F, or G. So studying and only studying causes you to do better on an exam, not how much caffeine you had, not what you ate for breakfast, not how much sleep you got. So we are going to hold all those other things constant. The only difference we want in an experiment is whether or not you studied, so the levels of the independent variable. Whether or not you studied, whether or not you slept, whether you had the antidepressant or the placebo. Those are the only things that we want. We want A and only A to cause B. So everything else becomes constant. The only difference we want between the groups is whether or not you actually studied. So looking at a lot of the similarities and differences and are good study tools. But I also provide study guides. So descriptive statistics, descriptive research is to observe and record behavior. We use 3 different kinds: case studies, naturalistic observations, and surveys. Nothing here is manipulated. We're not putting people into groups based on different things. Normally, we're only using, if it's case studies or naturalistic observations, only looking at one person or one small group of people at a time. Surveys and interviews is where we're looking at a lot more people in less depth. What is the weaknesses here? If we can't manipulate anything, there's no controlling of variables. And of course, one single case that a person has cannot be generalized to other people, even if they have the same disorder, disease, quirks, whatever it is. In correlation, we are trying to detect a naturally occurring relationship So we are assessing how well one variable predicts another, or how well one variable or one factor is linked to another. So we collect data on two or more variables. We're basically measuring two things. I like using the example of crazy cat person. So you can see if that's an actual thing by measuring the amount of cats a person owns, and then measuring how sane or insane they are on some sort of test. So we can collect data on one, and it doesn't matter if we measure the number of cats first, or if we measure how sane or insane they are. But nothing is manipulated. We're only measuring two things. And with that, you cannot specify cause and effect. But again, the higher the correlation, positive or negative, the more likely that there is some sort of cause and effect. So a lot of times those numbers or those correlations that are very, very positive or very, very negative can be assessed by using and turning them into an experiment. But in experiments, those are the only ones that explore cause and effect. Remember, correlation does not imply causation. In this case, you are manipulating one of the factors into a control and an experimental group, and you're using what we call random assignment. The reason that we use random assignment means that you are not just taking people on the right side and putting them in one group and people on the left side and putting them in a different group. You want to randomly assign so that they have an equal chance of being in either group. And the reason that we do this is because there may be a reason why people sit in the front or back or on the left or right side. So for example, let's just say everybody that comes in first is on my right side, right? They come in early to class, ready to learn, books out, pencils out, notes ready, you know, whatever. And they just seem to have maybe better study habits, and that's why they're there early. The people on the left are the ones that are scrambling, coming in late. Maybe they don't have their book even yet. They don't have anything to write with. And so if I put the people on the right that are ready to learn in the exam group, the studying group, and I put the people on the left that don't seem prepared, and I put them in the control group that doesn't study, there may be a difference in their exam scores before I give them the manipulation. The people on the right may get better scores on an exam whether or not they study. The people on the left may get worse. So then I don't know if it was actually the studying that caused them to do it or because they were better students, right? So in this case, if we randomly assign them into one group or another, right? I'm randomly going to pick you over there to be in the group on the right and you over there to be in the group on the left. That way, we have more of a chance of equal numbers before we even ask them to study or not study. So what do we manipulate? We manipulate the independent variables by putting them into at least a control group and an experimental group. The control group would be no studying. The experimental group, again, would be studying. This is the best way to assess cause and effect. We hold the other things constant, like amount of sleep, what they had for breakfast, whether or not they had caffeine. Obviously, putting them in a lab setting, it's always the same temperature in the room, same time of day, no distractions, right? So what are the weaknesses of experiments? Well, sometimes what we're trying to do is not feasible. You can't always experiment or test everything. We know, just kind of like with descriptive, that sometimes results may not generalize. What happens in our class may have happened in our class, but may not happen anywhere else. And sometimes it's just not ethical to manipulate certain variables. I'm not going to ask people to, let's just say I came up with a treatment to stop smoking, right? I'm not going to ask people to start smoking just so I can get them to stop smoking, because that's not ethical to do. And we want to ensure that we have the participants' safety in mind. Now, there are some studies that happened back in the day that we didn't have these ethical things, and you know, things can get pretty scary. We got real raw results, but the trade-off is that people weren't necessarily feeling like they were safe. And nowadays, we make sure that that's in place. So the purpose of experiments, again, we're not looking to see why Sarah does what she does or why Henry does what he does, but we're trying to test everyday theoretical principles. Why do people in general get upset in this setting? Why do they get mad in this setting? Why do they get scared when they do this? Why do people do what they do? We're looking for principles of why people or humans do things in general, not recreation of everyday life behaviors. Another reason we can use a sort of artificial setting. The resulting principles that we get from these experiments help us to explain people's overall everyday behavior and not very specific things. Again, not why Henry does what he does or Sarah does what she does. Because in psychological science, our focus is on looking at the principles that explain many overall behaviors on a daily basis, not very specific things, right? Not why one or two people get upset by this, but the rest of the world doesn't. We want to know why people in general do what they do. So the question remains that a lot of people ask, can lab experiments illuminate everyday life? Well, the answer is yes, because we can control for things like what you eat, how much you sleep, how much caffeine you have, how much light, how much distraction there is. So even though they're artificial environments in lab experiments, they're meant to test general theories. And we don't know if people are going to be distracted by things in the real world. So when we're trying to look at general principles for everyday behaviors, then lab experiments can be really well done. And when we're looking, remember we use that word replication, when we're looking to replicate these experiments, then a lot of times we can go into real world settings to see if it works. Okay, great, you can take a test in an artificial setting where we can control for how much you eat or sleep or things like that, but what about when we're trying to see if it works in regular everyday school? Then we can do it without these things and see if it still holds. Another sort of debate that we could get into, which we're not at liberty to do necessarily in an online format, is talking about in psychology and biomedical studies that we use a lot of animals. And the reason for that is because you can't recreate the human brain in artificial things like computers. For the most part, they can't think like humans. They can compute, but you can't get them to think and reason and act like humans. Animals, as we'll talk about in the next chapter, actually can, at least on a lower level, that we can sort of look at their behavior. We can't ask a mouse or a rat or a pigeon or a monkey, how they're feeling about certain things or if they're scared, but we can look at their behavior in certain situations, or we can give them medications for things in certain situations and see if it helps. So I'll get more into that in chapter 2. But when asked, is it right to place the well-being of humans above that of other animals? And again, before you think about answering and things like, well, what about criminals? Well, if you think about a control group and an experimental group, people that are in prison or things like that may not necessarily be what we would deem quote unquote normal in society. So they may be compromised to begin with. And second of all, it's just unethical to do things on humans, whether or not they broke the law, right? So the response to this question varies by cultures. We talked about cross-cultural psychology. In North America, Canada, and the US, about 60% of people said that medical testing on animals is morally acceptable. Of course, this isn't the same argument when we talk about testing for makeup and things like this. We're talking about advancing treatments and science of diseases like Alzheimer's, Parkinson's disease, right? Things like that. In Britain, only roughly over a third of the population, 37%, agreed. So it depends on who you talk to and where you go. One of the things that people don't realize, though, is that we have a lot of safeguards in place in these countries that practice this, and that most of the times animals get treated better than humans. I know because part of my PhD program was working with mice, and if they have so much as a scratch on their paw, they can't do any testing. They're exempt from all of that and go on to just live their lives. So what safeguards should be there to protect animals in research? again, you see this response varying by culture. Anything that has primates, dogs, or cats, and primates are still used because genetically, DNA-wise, and genes, they're 98% or more similar to humans, whereas other animals, dogs, cats, rodents, are a little less, but still pretty close, still up in the 80 to 90% range. But 98% support some sort of government regulation for protecting primates, dogs, and cats, and 74% still support protection for rats and mice. Of course, if you saw a rat or a mouse in your house, you would try to kill it or get somebody to come kill it right away. But that's, I'm not arguing those things. The point is that we do have these safeguards in place. Just like humans can't be asked certain questions or have to make sure that they're taken care of, same goes for animals. And they're actually, in most times, like I said, treated better. They're, the rooms where they're kept in research labs have to be a certain degrees. It's like 70 degrees. They have to be fed unless food restriction is part of the experiment. Again, if there's so much as a scratch on them, they are eliminated from the research. So there are a lot of safeguards in place, and a lot of times I can tell you they're treated better than most humans. So universities for humans have what we call IRB, or Institutional Review Board committees, which includes lab regulation and inspections regularly. Humans have to have informed consent. In the UK, there's the British Psychological Society, or BPS, which has guidelines for this. In the US, we have the APA, or the American Psychological Association. This tells us what is humane and not humane treatment, minimization of illness, pain, infection. And in Europe, Parliament actually has standards for animal care and housing. In the US, we have what's called an Animal Research Committee, or ARC, A-R-C. It's a little bit different from IRB. IRBs are for human subjects, and the ARC, the Animal Research Committee, is for the well-being of humans. So it's not the Parliament, it's not our government system that tells us. It's a different subsection that helps specifically with animal studies. For humans, I'm just going to go over this real quick. I'm not really going to test on this, but ethics codes say that we need participants' informed consent so that they know what they're signing up for and we're not surprising them or, right, exposing them to something. We're protecting them from any harm and discomfort, which could even mean as much as like getting angry or bored. Information about individual participants is kept confidential, so Jane or John or Lewis or whoever, their names, their identifying information is completely stripped, and they become subject number 1, subject number 6, subject number 192. So nothing is ever traced back to them. So that's where we encourage them to tell the truth, because nothing ever gets back to them. Nothing is connected with their names. And of course, they're fully debriefed after to tell them what the study found, explain the research, and what they were doing. So they get the full synopsis and as much protection as possible. So where's the value in research? When we are looking at these things, what do the numbers tell us? And what are these numbers? Well, we can affect what is studied. We can affect how it's studied, how many hours of studying, how many hours of sleep, how much of the medication goes into these people, and how the results are interpreted as well. Sometimes we don't find an overall number that works, right? Maybe the people that studied scored about the same as the people that didn't study. If you, on average, the ones that studied scored 38 right, and the ones that didn't study on average scored 33 right, is that a big enough difference to say that they scored higher or lower? Well, we can use statistics to figure out how the results are interpreted. Or if we don't find what we're looking for, maybe we can split it up and say, well, let's look at females and males that studied and didn't study. And now, boom, we get this big effect. And it goes into that gender psychology thing. We can color the facts the way that we see them or break them up into different categories. And this can be influenced by the popular application of psychology to see what's going on. It could play into stereotypes. It could play into cross-cultural. Are Asians going to score higher than African Americans or Caucasians or Asians, right? or, some other Pacific Islander or something like that. So you have to be careful a lot of times with looking at the numbers and what they actually mean, because we don't want misleading information, and the world is already full of this. So we need to look at statistical reasoning and be very straightforward about it. Again, I'm not going to ask you to do any math, so don't worry about that. But we need to understand that accurate statistical understanding of this data is very important. Big casual estimates often misread reality and misinform, like people think that there is a huge difference in gender. And like we talked about in the prologue, it's actually the more important or more interesting aspect is that we are more similar than we are different. These big, round, undocumented numbers, right? If you get these really big, specific numbers, a lot of times we get, decimal points, 60.7, 72.4. If you get 50-50 or big, big round numbers, it warrants caution that maybe they weren't done the right way, or maybe people are estimating in the wrong direction. So that's why teaching statistical reasoning is needed, and how we present the information needs to be understood and needs to have more transparency, so you can see the way that it's processed. When people do research and they write in journal articles and they publish their findings, it has to get what we call peer reviewed, which means that people who are other people that are experts look at the numbers and they look at the way that they got them and they say, yes, this was the right way to do it. Because otherwise, you could be misleading, like that original study on autism and vaccinations, right? It was later thrown out and proved to be false and fudged, like the guy made up the numbers that showed it. So we need a good understanding. We need it to be peer reviewed. We need people to understand where the numbers come from and how. So we use measures of central tendency. When you're talking about individual people on a case-by-case basis, that can vary wildly. But when we do these experiments and put people into groups of experimental versus control groups, we need to take a measure of central tendency to compare these groups to each other. How did they do on average? So the mean, which you see in the middle here, is the one that we use the most. This is the arithmetic average of a distribution, which is often obtained by adding up all the scores and then dividing by the number of people per group. So if there's 20 people in a group that studies and 20 people in the group that doesn't study, we take all of the scores and add up all the 20 people in the group and we divide by 20, and that gives us our average for the group. So again, let's say that the average for the people that studied was 38.3, and the average for the people that didn't study was 32.6, right? Then we compare those two using a statistical program, and it will tell us if these answers are far enough apart, or these numbers are far apart enough from the other group to be considered a significant difference. The problem with the mean, which I'll explain in a couple minutes, is that it can be distorted by a few really high or low scores. So it's really susceptible. This is why we need transparency. It's really susceptible to a possibility of extreme scores that can change the whole outcome of these numbers. The median is the middlemost score in a distribution. So half the scores are above it and half are below. If we have a group with 20 people, or 21, let's use an odd number, 21 people, it would be the 11th score, would be the median, whatever that middle score is. There's 10 below it, 10 above it, it's right in the middle. So the median is only affected by how many people are in this group, right? But it's pretty much always going to be right in the middle, the middlemost score. So this one doesn't really get bumped by higher or lower scores, just by how many people are in the group. The mode is the most frequently occurring score in a distribution. So if you have 20 scores and 10 of the 20 people scored 40, and nobody, none of the other numbers were as much as 40, 40 is your mode. So that one is relatively unchanged, right? Unless you get more people and then somebody scores 38 12 times, then that's going to be the mode, right? So the mean can be distorted by a few scores, and that's the one we use the most, so we have to be careful. The mode and the median are pretty much steady right in the middle or whatever's the most frequently occurring score. So let me show you what I mean about the mean. So here we see a graph of people in a village, and let me see if I can move this down. If there's, I don't remember if there was a, yep, skewed distribution. Okay, so let's go back. Here we see the average income of families on this, in a village in this case, but we'll just use modern day terms, one neighborhood or one street. Some streets, especially in East LA, are a little lower income than some other streets. So in this case, on this street or in this neighborhood here, we have, these are the annual income per family in thousands of dollars. And each of these people sitting down, holding their knees in green is one family. So what we see here in this distribution, this is the normal distribution. Most people fall in this range. We have two families that make $30,000 on average a year. We have 1, 2, 3, 4, 5, 6, 7 families that make $40,000 a year. 4 families that make $50,000. 4 families that make $60,000. 3 that make $70,000 and $80,000. 2 that makes $90,000. 1 family makes $100,000 a year. This is where majority of the numbers are. Now you see, here's the mean at $140,000, which is way past this whole distribution. That's because there's 3 families on this block. 1 family makes $180,000 a year. 1 family makes almost $1 million a year. And here, this family here makes $1.4 million a year living in this neighborhood. And those 3 extreme scores, or at least 2 of those 3 extreme scores, can really move the mean out here. When almost everybody in the neighborhood makes less than $100,000 a year, if your average is $140,000, this is a really misleading distribution, right? So this graphic representation of a village's income illustrates the 3 measures. Here, if this is the normal distribution, let's just ignore these for a second. Between 30 and 100,000, 60 is going to be in the middle. That's your median. There's 3 below it. There's 4 above it or so, right? That's in the middle. The mode is going to be the same. There's 7 families on this block that make, in this neighborhood that make $40,000 a year. That's your most frequently occurring. That's your mode. It's going to be relatively unchanged. If your mean is based on this distribution, your mean is probably going to be around 50 to 60,000 a year. But these 3 extreme scores over here push it all the way over, because if we're taking the average of everybody and then dividing it, these scores are going to have a huge influence on your average. So this person makes 180,000 a year. Maybe they got a good job and they just decided to stay. Here, this person, maybe they have a family member that was, you know, playing sports or something like that, and now makes 950,000 a year, became a lawyer, something like that, but they wanted to make sure they still lived with mom and dad and are just, you know, rebuilding on the block and making a really nice house. And this person makes almost $1.5 million. Maybe this person plays sports and got a really nice contract, and they don't want to forget where they come from, right? But if we take all of these scores into account, it's going to make it look much more inflated. It's going to say that this average village or this average neighborhood makes 140,000 a year, when majority of its people are less than 90,000 a year, right? So it can be skewed and moved by just a few extreme scores, and it looks deceptively high. So in this case, what we would do is we'd probably just take these cases out, and your mean would move back over here. So it's very sensitive to these extremely high or low scores. That's what I mean by that. So what measures of variance or variation reveals how much similarity or diversity there is in scores? When we look at the range, that's just the difference between the lowest and highest score in a group or in a distribution. And we use a measure called standard deviation. Standard deviation says if there is a mean, or the average is, let's say, you know, on a score of 0 to 100, the average is 50. How much does each score vary above or below that mean from a normal distribution? So if we go back to this last slide, this would be the normal distribution. These would be the extreme scores that we might eliminate. But a normal distribution is a symmetrical bell-shaped curve that describes the distribution of the data. And what it says is that 2/3 or 68% of the scores are going to fall within one standard deviation of the mean. And that within 2 standard deviations of the mean is going to be about 95% of the population. So you don't have to understand what that means right now, but I'm going to attempt to explain it. Here is a normal curve. Anybody up, and let me move this down again. I don't know why it does this, but I'll bring it down. Here we go. And back here. And what we see here is an aptitude or an IQ test. And if anybody, I don't know if anybody's ever taken an IQ test. There are 2 main IQ tests that people take. One is called the Stanford-Binet test, which was originated at Stanford University. And the other is this one called the Wechsler Intelligence Test. In the Wechsler Intelligence Test, what they do is they standardize the scores, and you don't need to know what that means, don't worry. But what it does is it gives us a nice round number for the average. So on an IQ test, when they standardize the score, that puts the mean at exactly 100. So if you have an IQ of 100, that puts you right in the middle at the 50th percentile. In this, they say that the standard deviation is about 15 points. So a standard deviation could be 15 points above or 15 points below. So one standard deviation with a score with a mean of 100 is going to be from 85 to 115, 15 points below to 15 points above. So what that says is that 68% or 2/3 of the population is going to fall within one standard deviation above or below the mean. So 68% of people that take this intelligence test will score between 85, one standard deviation below, and 115, which is one standard deviation above. And it goes further to say that 95% of the population is going to be within 2 standard deviations of the mean. So 2 standard deviations down would be 70 on the low side and 130 on the high side. So within 2 standard deviations, majority of the population is going to have an IQ between 70 and 130. That leaves about 2.5% below 70, 2.5% in the genius range above 130. So because 95% of people fall within 2 standard deviations of the mean, we can be fairly confident that we can be 95% confident that people will fall within 2 standard deviations. And the rest of it are what we call outliers. So when we say that something is statistically significant, we're using these means and standard deviations as our markers. So we're saying that we have a 95% chance that what we actually found was correct, and only a 5% chance that it was due to some sort of error or mistake or chance, random chance. So when we ask, when is an observed difference reliable? Well, first of all, a biased sample is never going to be preferred over a representative sample. So we talked about this in descriptive statistics. We want to use a random sample. In experiments, we talked about randomly assigning into one group or another. If we know that there's about an equal chance of people being in one group or the other, then it is a representative sample, instead of just saying everybody on the left side versus everybody on the right side of the room. Less variable observations are more reliable than more variable. So if we get a huge difference in scores and difference in individual differences in people, it's better to have less variation between groups, or within groups, I should say. And of course, all things being equal, more cases are better than fewer cases. So again, I go back to those studies on vaccinations and autism. The first original study that was, again, proven to be false and debunked was based on 12 people. The ones that hold up are based on more than 95,000 people. More cases are better than fewer because it shows the numbers will be averaged much better. Generalizations based on a few unrepresentative cases are especially unreliable, like that vaccinations cause autism original study from 1996. When we do get a difference between groups, let's say that the group that studied on average scored about 40.1, and the group that didn't study on average scored about 29.8. if we get this, run the statistics and we find that we say these differences are statistically significant, it means that we've taken the averages and that they were reliable and the difference between them was large enough for us to say with 95% confidence that the numbers we reached were correct and the numbers were far enough apart to say there was a difference. Those that studied scored significantly higher than those that didn't study. This observed difference is probably not due to some sort of chance variation or some sort of random error. And so in psychology research, our proof beyond a reasonable doubt means that there's less than a 5% chance that this occurred by accident. So we are more than 95% confident. We go back to that 95% here, right? This tells us 95% confidence, right? So to say something is statistically significant, that proof beyond a reasonable doubt means the odds of it occurring by chance are less than 5%. That is chapter 1. There will be an assignment based on this that you will be doing, which will be due Sunday. And good luck. I hope that I made these concepts clear. And once again, I will talk to you soon.